Now let's come to the topic where we talk about the second law efficiency illustrations. Now the second law efficiency of different components can be expressed in different forms. Now the basic fundamental that we use here is the exergy balance that we talked about in the previous video. Now the first illustration is the turbines. So this is a turbine in which you have some heat inflow and some work outflow in the form of some shaft work. There are two sections, section 1 at the entry and section 2 at the exit. Now you can easily apply the steady flow exergy balance onto this. Okay, so for a single stream, if you remember, the steady flow exergy balance was Q dot upon M dot into 1 minus T naught upon T sigma plus you had AF1 minus AF2 minus W dot upon M dot is equal to I dot upon M dot. Okay, now if you take all the negative terms towards the right hand side, this would give you Q dot upon M dot into 1 minus T naught upon T sigma plus AF1, this is equal to AF2 plus W dot upon M dot plus I dot upon M dot. So this is what you get when you rearrange this particular equation. Now if I assume that there is no heat loss, so this whole term would become 0, given that the turbine is adiabatic. You can put an insulation out on the casing of the turbine, so this means there is no heat loss. So this equation would be reduced to AF1 minus AF2 is equal to W dot upon M dot plus I dot upon M dot. Now if you look at this particular term, this is basically the maximum availability or the maximum amount of work that is possible from this turbine. Alright, and if you look at this is the actual availability. So when you have to write down the expression for the second law efficiency, it would become the minimum availability upon the maximum availability, and the minimum availability is equal to the actual work upon the maximum possible work, and that becomes equal to W dot upon M dot divided by AF1 minus AF2. So this is the expression for second law efficiency for a turbine. Alright, so I hope you understood this much. So let's carry on the same analysis and now talk about a compressor and a pump. So the second illustration is for a compressor and a pump. Alright, now if you go back to the analysis of turbine, let's rewrite this particular equation again. So you will have Q dot upon M dot into 1 minus T naught upon T sigma plus AF1 minus AF2. Alright, then you have minus W dot upon M dot, this is equal to I dot upon M dot. Okay, now because it's a pump and a compressor, this signifies negative work input, isn't it? So there is no shaft work, there is only input of the work. So, and we can also assume it to be adiabatic in its operation. So given the adiabatic operation, this whole term would become 0 and this would become plus because it has to be a negative work. So you can put a negative sign over here. So you will get AF1 minus AF2 plus W dot upon M dot is equal to I dot upon M dot. Alright, so from here you can say that W dot upon M dot is equal to AF2 minus AF1 plus I dot upon M dot. So this is what you get for exergy balance in the case of a compressor and a pump. Alright, so now in this, these two terms are changed. Alright, so because if in this the work is the input, alright, and this is the output, so this becomes my exergy input and this becomes my exergy output. So the value of the second law efficiency becomes AF2 minus AF1 divided by W dot upon M dot. So if you have to take it as AF1 minus AF2, now it will become more sensible to you, because now you will have negative value of work, and that is what it signifies, that a compressor and pump has negative value of work. So this is the formula to note down for the second law efficiency of a compressor and a pump. Now let's go to the next illustration of the second law efficiency, and that is heat exchanger. Now in a heat exchanger, the single stream concept or the single stream analysis is not there, because there are multiple streams. Alright, so let's draw a diagram first of all for it. So let us say we have a very simple looking heat exchanger. Alright, now in this there is some fluid which is flowing. So let us say this is the cold fluid that is flowing. Alright, and the hot fluid is flowing from top to bottom. So this is MH dot and this is also MH dot. Alright, and let us define these sections one by one. So this is section 1, this is section 2, this is section 3, and this is section 4. So there are multiple streams that are going in and out of this heat exchanger. So the single stream analysis is no longer valid. So for this we will have to apply the concept or you can say the generalized rate equation. So you'll have summation 1 minus T naught upon T. Let us say there are J components, I'll say J, into Q dot J minus the work flow rate from this control volume, plus now you will have the input. So the input is at section 3 and section 1. Alright, so the total input due to these masses would be M dot H into AF1 plus M dot C into AF3 minus the outlet is at section 4 and section 2. So you'll have M dot H into AF2 plus M dot C into AF4. So this is what you get is equal to I dot of the control volume. Now because it's a heat exchanger, so let us say it is again insulated from the outside, so there is no heat loss from the boundary of the heat exchanger. So I can say that this value will become 0, and also there is no shaft work involved, so this will also become 0. Okay, so the whole equation then becomes, after combining M dot H and M dot H and then combining M dot C and M dot C, so you'll get M dot H into AF1 minus AF2. Alright, this is equal to this is equal to, you can take the m dot c onto the other side, we'll get m dot c into AF4 minus AF3 plus the irreversibility for the control volume. Now if you analyze this particular equation, this is the exergy which is in, and this is the exergy which is out. Alright, so as per the definition of the second law efficiency, it is exergy out by exergy in, and this will be equal to mc dot into AF4 minus AF3 divided by m dot h into AF1 minus AF2. So this is the equation to note down for the second law efficiency of a heat exchanger. So I hope you understood this analysis as well. Now after this, let's go on to the last illustration of the second law efficiency. That's the fourth illustration, and talk about the mixing of two fluids. The mixing of two fluids. So let's draw a diagram for this. Okay, so you'll have paths like these, and let us say these paths are insulated from the outside. So it's a given that Q would be 0, and again it does not involve a single stream analysis. You'll have multiple streams for it, so we'll have to use the generalized rate equation for the exergy balance in a steady flow. Alright, so let's have this as section 1, this as section 2, and this as section 3. Now let us say there are 3 streams for it. So one is this, the other is this, and the third one is this. So let us say this is the hot stream. So this is the hot stream of fluid. Let us say this is the cold stream of fluid. Okay, and you get some mixture at section number 3. So let's give it a name. So let us say hot stream is flowing with a mass flow rate of m1 dot. The cold stream flows with a mass flow rate of m2 dot, and the mixture comes out with a flow rate of m3 dot. Okay, so now as per this particular diagram, let us write down the general rate equation of the exergy balance for this mixture. So you'll have 1 minus T naught upon T sigma into Q dot upon m dot. Okay, now let's quit this m dot for the moment, and let's use these masses for their respective streams. So you'll have plus m1 dot into f1 plus m2 dot into af2. Alright, now the other side will have the work transfer through the control volume plus m3 dot into af3 plus the rate of irreversibility and the control volume. Now the mixing is an adiabatic process, so this will become 0. Also there is no work flow from the system, so this will also become 0. Okay, and we can say that whatever mass flow rate these two streams are getting, this is the sum. So m3 dot is equal to m1 dot plus m2 dot. Alright, so you can put the value of m3 over here. So you'll get m1 dot into af1 plus m2 dot into af2 is equal to m1 dot into af3 plus m2 dot into af3 plus I dot CV. So this is what you get. Okay, so let's bring the M2 on the other side and M1 on the left hand side. So you will get M1 dot into AF1 minus AF3. This is equal to M2 dot into AF3 minus AF2 plus I dot CV. Now again, if you look at this equation, it is very easy to conclude that this is the exergy in and this is the exergy out. So the second law efficiency for the mixing of two fluids would be M2 dot into AF3 minus AF2 divided by M1 dot into AF1 minus AF3. So this is the complete analysis of this illustration of second law of, or you can say the second law efficiency. So I hope you understood these four analyses of the second law efficiency. So this finishes the whole topic on the concept of available energy, availability and irreversibility. Now let's look at some questions on this topic.